Hello, this is my lab report for Lab 5, Faraday's Law. This lab focuses on observing and analyzing a falling object using Faraday's Law. After our experiment, we'll create a Glowscript model that visualizes a falling magnet. Some of the key principles that we'll use are Faraday's Law, position update, and magnetic flux. A preview of our result: our observed fall time was 1.43 seconds, and our simulated was 1.57. Our key principles. So here we can see the magnetic field produced by a dipole, and then the magnetic flux, which is pretty much how much magnetic field goes through a given area, a given surface. Then there's the derivative of the flux, and finally our force, which is the force of a current carrying wire, which is I L cross B. Assumptions and reasonings. So for simplicity, we'll say that there's no air resistance, friction, or collisions, and we'll also say that the only forces we need to account for are gravity due to the Earth and from whatever we observe from the tube. And finally, we'll say that our bar magnet can be treated as a dipole. System versus surroundings and initial conditions. Our system is our falling bar magnet. Our surroundings are the Earth, the aluminum tube, and everything else. Our initial condition is when our bar magnet is held at rest above the tube. Experiment process. We start by getting the geometry of the tube of aluminum foil. Then we'll also analyze our bar magnet to get the mass and the dipole moment. Next up, we will hold the tube upright and we'll drop the magnet through it. And we'll time how long it takes for it to reach the bottom of the tube, and then we'll repeat the process and get an average. Coding process. We start with our constants and then we move on to our geometry and our parameters for the model. Next up, we have two functions. One returns a magnetic field given a dipole moment and a position vector. The other calculates the derivative of the flux, the magnetic flux. Next up, into our loop, we'll go through every little segment of our tube and we'll calculate the rate of change of the flux. Then we can calculate the current by just dividing that result by the resistance. Finally, we can calculate our magnetic force acting on our bar magnet. Then we can find our net force by adding that together with the gravitational force. Next up, we'll do our position update and update our graphs using kinematics. Now for our analysis. By Lenz's law, we know that the current above our bar magnet is clockwise and below is counterclockwise. Now what would happen if we flipped our magnet around? Nothing much, the time would still be the same. And then there was a slight difference between the time we measured in our real world, in our experiment, in our computation. So we can make our computation more accurate by decreasing our time intervals or getting more precise measurements. Now for our velocity time graph. We can see that when we're at the top or the bottom of our tube, gravity wins, but in between, the gravitational and magnetic forces cancel out. This makes sense that the magnetic force is strongest in the middle because it gets contributions from the current both above and below the bar magnet. Sources of error. There could have been issues from human measurement or from idealized assumptions. What if the resistivity of our conductor was close to 0? Well, since I equals V over R, our current would increase, and because magnetic force is proportional to current, our magnetic force would also increase. That means our falling bar magnet would have a slower terminal velocity. What if we cut holes into the side of our tube? Well, those would disrupt the current, which would decrease the magnetic force. In conclusion, we have found that Faraday's law and the changing magnetic flux can lead to very noticeable effects, and that electricity and magnetism are closely related.